Yo, gonna do an unscheduled Friday stream. Started here. Let's see. Change the name. Manage. All right. Tonight we're going code spelunking. There's no real goal here. Just exploring. Also, I've got some changes to audio setup, so interested to hear how all that sounds. Interested all that seem to sound okay. All right. Anyway, so there's no real goal, but something I was kind of thinking of. We had started looking at some disassembly for this code, for this LeetCode challenge thing that we had solved. And let's see if I open that disassembly again. There's some things about strings and trying to use SIMD that still haven't quite satisfied all my curiosity. So yeah, I'll still try to satiate my. Did switch over from using the MSVC compiler to using Clang. That I think that assembly is a little that disassembly is a little easier to read. And this is the thing that I'm interested in right here, these registers. I want to look up what those are. So what are the XMM registers? What are XMM registers? XMM registers, this is Stack Overflow. My desk is so cluttered, I don't really have a place to set my coffee. That kind of sucks. So, all right. XMM register. Assembly. Yeah, shuffling. Yeah, so I think the XMM registers are associated with single instruction multiple data. I don't know 100%. That's why I'm like, yeah, okay. So one thing I especially didn't know is that string had any association with it. And one thing that kind of sucks is in MSVC or in Visual Studio, we can see the normal registers, but I don't know if we can see the XMM register. So let's also get an answer to that. Visual. Ah, right click inside the registers window and check the items to display. Okay, okay. So if we do this, okay. So now we can see those additional registers. That's cool. Okay. Oh, okay. So I turn on the MMX. That's not what I wanted. I wanted the SSE because like now you can see here's XMMO, XMM0, and that's what this disassembly is working with. So that's cool. All right. So I have no idea what this instruction does. I also have no idea what this instruction does. So there's some more things to look up. Probably I'm thinking this is exclusive or pointer string, maybe? Just wild ass guess. Zorps. All right. So there's a Stack Overflow question with like probably one that we would be asking anyway, or I would be asking. Is like, why is it calling this on itself? I think that probably clears it out. Keep pulling up the wrong browser. Okay, here we go. So we do have that question. Oh, packed single precision. Okay. Performs a bitwise logical OR of the 4, 8, or 16 packed single precision floating point values. Okay. Packed single precision. Okay, the packed part means single precision is just like a normal float versus like a double. Uh, but packed means like there's a bunch of floats all packed into this register. That's how I understand. Right. And then what is the point of doing a XOR on the same thing? Okay, clear the possible garbage values. All right. So the thing is that you just want to. It sounds like it just wants to make sure this whole thing is clear. So probably if we do, if we step through a little bit, probably after this operation, I would expect this register to just be all zeros. Oh, didn't hit what I thought it hit. Yeah. Okay. Neat. Uh, and then what's move? So this is probably packed single precision again, but I don't know what the A means. So what is move APS? Move aligned packed single precision. If we really wanted to know these things, we should probably like look it up in like the LLVM reference. I'm sure like if I do or it might actually be more related to the like the AMD reference. Like, yeah, we're just gonna take this one. Not trying to be too precious about this since I don't really know what I'm doing. Uh, so move aligned moves 4, 8, or 16 single precision float from the source operand to the destination. Okay. So when the source or destination operand is a memory operand, the operand must be aligned on 16 byte thing, 16 byte boundary. So that's the byte alignment thing that we were talking about a couple streams ago. Basically, the address has to be a multiple of 16 for it to be 16 byte aligned. Okay. So with this, so what I think what this is saying then, this is opposite of what I was expecting. So it's almost like it's saying move 0 into the first. Oh yeah, I think that's what it's doing. I think it's like initializing a spot. So if we go to watch, like uh, test, so I'm just getting the address of this vector. Kind of annoying that when you copy value, it copies like everything. It'd be cool if there's a copy address. So I'm not totally sure what that's telling us right now, but let's just hit step and see what happens. So we want to go back to our register view. Ah, okay. So here at memory, we're looking at the address location of the vector test, this vector, and it just moved. So it just moved the value that was in this XMM0 register, which was 0. It was made 0 on this line. It just moved that into the address. Probably yeah, we know from like looking at other things before that like what this like brackets test means is it's like basically put null in the first string of this vector. That's kind of how I understand it at this point. And then I don't know what this line is doing. I think, yeah, I have to look this up. I think with well, no. No, it looks like LLVM or Clang is still using RSP as the stack pointer. I don't know what it's doing with RBP. Let's look. Like some registers have conventional uses. Like RSP is conventionally the stack pointer, and RAX is conventionally where values are returned. Like when a function returns a value, it pushes it into the RAX register. So I don't know if RBP has a conventional use, so I'm going to look that up. RBP register is the frame point. I always get a little bit because I get a little bit confused between the stack pointer and the frame point. RBP is the frame pointer in your generated code. It gets a snapshot of the stack pointer so that when adjustments are made to the stack pointer, okay. That's fascinating. So so when adjustments are made to the stack point, so the stack pointer kind of moves around, like offsets from the stack pointer to certain values, with those offsets would have to change as the stack pointer moves around. But if you instead store like if you go into a function and you store where the stack pointer is so that then you can make adjustments to the stack pointer. That's what kind of like this guy is saying, like you're pushing values onto the stack when you enter a function. If you before you do that, if you store the stack point, copy of the store, blah blah blah. If you copy the stack pointer into the RBP, then any offsets you were going to use can stay the same. Anyway, that was really confusing because I don't really know. I'm just speculating. I have a general sense of how it works. Okay, so when we're looking at the code, we know that RBP, so like here, RBP is semi-related to the stack pointer. So probably what this is doing, yeah, it's moving a value. So there's some kind of I would say probably some kind of variable that's at this address right here, this address minus 10, or that's hexadecimal, so that's actually like 16. Yeah, 16. I believe that's 16. So we can double check. Yeah, that's 16. Uh, yeah, so it's moving this to that location right now. So like if we take RBP, if we take the address of RBP, go, so it's right here, and then we subtract 16 from it, 16 bytes. Yeah. So we're right here. So minus 16 would be like, well, we can make this easier on ourselves by changing the width of this to 16. So if we go to our address, go back to our address here. Okay. And then we subtract 16 from it, that should be like right here. So what we're expecting on this line when we step over it is for this to be for this to at least to here, from here to here, it becomes 0. That's what I think. Okay, and it did. Okay. Now, why did it do that? I don't actually know. I don't actually know why it needed to move. There's no like labels telling me anything. For whatever reason, it decided it needed to move 0. I guess we'll just keep stepping through and maybe we'll understand why it moved 0 to that location. Okay. So now we're using in place back to push this string into the vector, and in place on C++, it actually it's going to call a string constructor. So I think pushback would make a copy. It would either make a copy or it would store. I'm pretty sure it stores a copy. But what this one does is it actually like literally is constructing a string and passing in this as like arguments to the constructor. Anyway, um, that's in place. That's the in place back vector. it constructs the thing you're pushing. It constructs the thing you're pushing onto the vector in place, like right there. So now what it's doing, I think LEA stands for like least effective address or something. Load effective address, not least. That would be dumb. Load effective address. Okay. And I think computes the effective address of a second. I think like this is kind of if you think of an array type thing, you have the base of the array plus some offset. That's the base plus that offset becomes your effective address, and that's the concept of what the load effective address is doing. So yeah, yeah. So it's going. So what this looks like to me is it's like going to do something here that I don't understand and put it in this register. R8, which R8 does have something in it right now, but it's about to get blown. It's about to get overwritten, blown away. So I'm curious if we take this right here and go see what's in the memory. Huh. That's really fascinating, right? This this kind of means like there's stuff going on in C++ that I don't know about that lit in place, but like this is really interesting. So we went to this address right here, and it's saying string too long, bad array, new length. I don't know. But I think what it's doing right here is it's constructing an array. It's constructing a string, and it's going to store the pointer to that string in R8. So if we go ahead and we do F10, I always have to look down to see my function keys. I don't have muscle memory on my. So if we go R8, so now there's something there. It's an address. Wait, yeah, it's that address we were just looking at. So, and when we hmm. So it did load that address, but I don't. This is so that's the memory address, and then here we can kind of see the contents, and I have no idea what those contents. But now what it's going to do is going to move the address of the first like element 0 of our vector. It's going to move that address onto RCX. So like, and we can kind of anticipate what that is by going to watch, and we can go like S0. There's a bunch of keys apparently I have to look at. Oh, out of bounds. Okay. Then is it going? And is it going to put this address in? That'll be interesting. Oh, geez, that's not what I wanted at all. So here we copy. I'm going to copy the value. It'd be nice if you could be like copy the address. Is it? Okay. So we're right here, and maybe this address right here is what's going to get moved into RCX. Well, I guess we'll step and see. Ah, that's not what I meant. So keep your eye on the RCX register. F9A. Okay, so that's what it did. And then it's going to this is doing that exclusive OR call again, which we know zeroes out. If you call exclusive OR on itself, it's gonna, as both the source and the destination, it's gonna zero it out. And EDX is short for RDX. Like, I think EDX is half of the RDX register. I think I know it's the same register, and it's like the lower it's the lower port half of it. But this is going to zero out the whole thing. Yeah. And then it's calling it's calling a C++. I don't think we're going to go looking. Anyway, so we know what that does. This is going to do the same thing. So let's go down and look. Let's go down and look at this XMM stuff. Yeah, more of this XMM stuff. It skipped over a lot. I don't understand what. I'm just overall confused of why it needed to do this, anything with these XMM. I think that will be something I have to research. Okay. But what I am interested to do is see, like, how can I load a string in how can I load a string into one of these registers and like manipulate it? I am interested in trying to manipulate a string using SIMD and so I'm gonna stop that and I'm going to try a couple. I'm gonna go back to my LeetCode problem. Oh, I didn't. Oh yeah, here we go. I want to copy this. And I want to this too. And yeah, then we're gonna compile this. And to make it a little easier on ourselves, we are not going to optimize. Now let's see if we taking off the optimization means like the code is gonna behave more like what we think it operates like. All right. So I'm interested to see what the disassembly here moves. So what is this disassembly going to do? This disassembly is going to, let's just step through and watch what happens to the registers. And then we'll go back to it to understand. So RCX is going to get the address of the first string. So if we go here and be like, said we were going to step through it. But we go F10. Okay. So now RCX should have an address. And if we go to that address, it's probably another address. Not totally what I was expecting. Let's keep going. XOR, we're going to clear out the RAX because EAX is like half. I'm pretty sure it's half. Like RAX is a 64-bit register and EAX is a 32-bit register. So it's going to clear out. It's going to clear out the whole thing. Are we compiling for 64-bit or? I'm wondering if we're getting in the weeds. Here we go. F10. Yeah, RAX cleared. And then it's going to move 0 into EDX. It's here, even though our EDX is already 0. Okay. And then I don't know what this means. Oh, this is it's calling the array operator. So I believe it's going to get the address of the first one, right? So it's going to be yeah, it's going to move this address right here, this 7B50. Going to move that into well, this call is going to return that address and it's going to put it in RAX. Okay. This is what I was talking about a little bit earlier is like the convention of the RAX register is for return values of a function to go there. So this is calling the array operator on the string. It's going to return the address of the first one and put it in RAX. So we'll watch it here. Well, before we do that, let's go ahead and get the. Oops. Oh, shoot. I did the wrong thing. Yeah, so ZY, so we can see where that. All right. So that address is going to end up in RAX after we hit step. Yeah. Okay. And then this is moving that address into RCX. Yep. 2. All right. And then this is going to call cstring, which returns a raw pointer to a raw pointer, a pointer to the character string. So yeah, it's going to put this address right here. This is going to put this address in RAX like we saw. Oh, no, interesting. That actually did rip, which right, that changed. That only changed this one. That's interesting. So I don't know what that totally means. There's a whole thing called like rip relative addressing. So it can be used for global variables only. You know, we always got to take Stack Overflow stuff with a grain of salt. Could be someone like me answering questions. uh, so I think what this tells us is that C string, the address of that C string is somehow relative to the RIP register, which is something like holds the memory address of the next instruction to execute. Okay. So anyway, point is returning the pointer to the character string didn't put it on RAX. It put it here, which is some kind of RIP relative addressing that I don't know much about. Okay. And now it's going to move whatever is in Rax, which was what we talked about. It's the address of that string. So the address of that first, it's the address of the first element in the vector. Going to move that into, so here we're taking the stack pointer and adding, what's 880 in hexadecimal, adding 128. I should probably adding 128 and moving it there. Wait, what is this? So we do, if we take the Rex thing, well, I don't, if we put that here, and then we do minus 0x80. See what happens. This just looks like it's like flip. We move RAX here, then we move what's there back. I have no idea what that means. My get RAX should be unchained. Yeah, I don't understand. It must be. I don't understand. I don't understand this. It moved the address. It moved the contents of the RAX register here to this spot, and then it moved that right back. So yeah, no, yeah. And now we're into the things that I think are interesting because right, we're trying to load the string into one of these SIMD registers. So let's go look at this is. Move aligned double quad word. The word I think is 2 bytes. The double word is 4 bytes. Double word is 4 bytes, so quad word would be like 16 bytes. We got 2 of those, so we're at like 32 bytes. $32, $256. What is a double quad word? Ugh, give me this. I mean, that's probably a good thing to look at, but looking for a shorter answer. 64-bit. Yeah. So a double quad word is 128 bit. 60. $16. So how did I end up with 32? Right. A word is 2 bytes, I think. Quad word would be 8 and a double is 16. Yeah, okay. So I must have done it in a different. Okay. So we're moving a double quad word. We're moving a 100. We're moving the contents of the RX register to here. That's what. Now, this is only 64-bit, right? Oh wait. Uh it it didn't move this. It didn't. We take REX, go there. Ah, so what it did was it moved all of this into that register. So what happens if the string had been longer? No, that's an address though. No. Is it? Take a look. I don't think that's. So 7A is 122. I'm willing to bet 122 is the ASCII. Really need to make a copy of one. Always. Well, not always. Not the first. Ah, I'm wrong. No, that's oct. I'm right. 122 decimals, 7A. We didn't even have to look up the decimal. So yeah. That's literally Z, Y, X. And this is C. This is all that stuff. Which I have no idea what this stuff is. What all that. Oops. So my question is what happens if the string okay. Uh, okay, so this is the address of this right here is the address of this variable. And in our disassembly, it's gonna move contents of, it's going to move the contents of this register to this address. Okay. So we should see this become the string that's currently pin. Yeah. Okay. So my question is like, what if the string is really long? It probably won't be able to move it in here. Let's see what happens. I think all this has to do is be more than 16. So, oh, oh, okay. Just gonna, doesn't really matter, but we're gonna. This is complete waste. Just because we're not actually like running the algorithm or anything. we're just we're just studying the code, spelunking. Need this one. All right. So let's go look at our disassembly. We're gonna step through all this. All right. Go check and see what's at RAX. Huh. Okay. RAX is a pointer. RAX is the memory address, right? And so it's like the it's the memory address of the first element of the string. So we go all the way to here. This one right here. Okay, that's fine. So what happens when we call this? And how come these guys have all of that in it? What? All right. 6 6 6 uh I need like 2 of these memory ones. So I only get, so it would have been helpful to count this. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 31. So 31. So right here at the end of the A, that's the first 16 characters, and that's all we get. in our variable. So, okay. So I think I have my answer to what I wanted to understand at this point is you can move a 16 character string into one of these SIMD registers. I think calling it's an extended register. I don't know if calling it a SIMD register, like SIMD single instruction multiple data instructions use these registers. So I'm calling them SIMD registers. You can move 16 characters, right? So how that relates to where all this started is I was like, well, could we do this algorithm using SIMD? And I think we can, but we have to take into the count that we would have to process each string in up to chunks of 16, which I think is still doable. Like, so the next thing that we want to figure out on this is how to do a comparison. Well, is that the next thing we want to do on this? Because the way the algorithm really works, actually, is that we're looking at each letter of a string and then going down. We're looking at the each letter of a string. So, well, yeah, we're like looking at this one, and this one. Right? So if I load this register, if I can load this string, I can load each of these in strings in their entirety into SIMD register, right? What does that give me that I don't already have? And I'm wondering, okay, so the next thing is to be like, is there a mask or some kind of, is there a way within the SIMD register? Like you got, this is in a register, this is in a register, this is in a register. Can you compare the first element of each one? And there's two aspects to this one that we realize is like, we can, these can be 16. And there's only 16 of those registers. So we can compare 16 characters and 16 total string. If we so there will be some logic here that we have to do in our code, uh, you know, to accommodate the the limitation register. So let's go back to the reference that we had. Oh, looks like I have some friends playing Fortnite. Sorry, sending a couple minutes. Sending a couple messages. Okay. There's a thing we looked at that had links that we right here. So this is where we got some of the ideas. And yeah, so here's how they're loading it in. Oh, I guess this one is just doing. So let's see. SIMD comparison. Hmm. Let's go compare. Let's go look. So we're looking at I think I might act been at this for like an hour now, and my brain is just an hour worth of stepping through assembly code that I don't know is kind of like a strain in my brain. I kind of want to like go offline and read this and come back, but after stepping through all this, I'm kind of feeling confident that there may be a SIMD way to solve this problem. Kind of interested to figure it out, but I need to go study some comparison. But what I might do is stop the code spelunking for now and switch over to some Fortnite. All right. I also kind of want to play Fortnite, but I also feel like I figured out some really cool stuff, and I want to keep looking at. Yeah, but I'm gonna look at it offline. All right. Question now is stream Fortnite? Hello? Friends are not online. Thought they were. Friends, where did you go? There's some kind of SIMD reference. This is Intel though. I have an AMD CPU. Does that matter? I don't think it does. And the fact that I'm asking this question means I don't know a lot about what I'm talking about, and it means I don't have it like I don't understand CMD that much. Like I think because it's all the same, it's like x86 64 architecture, like the way it works should be the same. But I find AMD has I appreciate AMD documentation a little bit more. I tried reading these programmer manuals before, and I feel like I understand the AMD ones better, to the extent that I can say I do understand, which is not. Okay, so this is the volume talking about the media instrument. Okay, so this is cool. No idea what I'm looking. No idea. Sure that the Intel Intrinsics Guide, SSE family. Right. So let's take a look at what we just used, right? Because we never looked at that. Yeah, I know I said I was gonna go game, but my friends are not online, so now I feel compelled to keep coding. Must keep coding. I mean, I am really curious to get this working. I feel like furthest I've made it in SIMD related stuff. I need to set up better fixes. So let's look up this one. We know what this is. We know what it did. So loads 128 bits of integer data from memory. Address must be aligned on a 16-byte boundary or general exception. That's something to keep. That's something to like look at and make sure like are we actually 16-byte aligned? I think we are, but we would just want to. All right. So let's. Okay. So let's say breaking out one note. Okay. Okay. Means you had to take a little break and wait for my tablet to connect. Move my coffee over here. My tablet serves as both a tablet and a cup holder. Okay. So let's say didn't turn on. Bad. Did I do? Is that copyright to say did I do that? I don't know. I forgot to turn on my. Okay. So come on, tablet. Come on, Mr. Tablet. I want to draw. There we go. All right. So if we have A, B, C, D, E, A, B, C, D, E, F, E, Z. Doesn't matter. Right. And we have this and we have this whole thing in a register. We have this whole thing in a register. This whole thing in a register. This whole thing in a register. And now with the SIMD, we can compare this entire contents of this register to the entire contents of this register, right? Can we do it such that it's comparing less than equal? Like, is A less than or is D is D greater than or less greater than A? Like, basically. Because like I think it can do, since this register is packed, okay, is packed meaning it has more than one like yeah, there's 3 elements in it in that single register. I think it can do, you know, compare it can do I don't want to say bitwise, kind of like element-wise comparison. We don't have to compare all like we're not saying is ABC equal to DEA. We can say is A equal to D, B equal to E. And maybe instead of doing equal, we can do less than. or greater than. So yeah, compare greater than. I'm willing to guess that I'm willing to bet what 50 cents that GT means greater than. So if we can, oh, and probably like the 16 means the element size. So 8 would be like a byte. 16 is 2 bytes. So you can compare byte wise. So probably like we would have to think about this, but we could probably use, oh no, we don't want that. We want one of these same things. So let's go take a look. Compare packed 16-bit integers A and B for greater than. So even though the register is 128 bits, right? And I should be able to do a lot of this math in my head, but I can't. I'm not smart like that. So if we do 128 divided by 16, that's 8. So there can be, within one of these registers, there can be 8 16-bit integers, right? And so what this is saying is compare each of those 16-bit things. So that's what we're trying to get, is all I'm trying to say. This is exactly kind of what we would need to solve this algorithm with SIMD. The only question is, oh no, and we fit 16, right? We know from looking at the step through that we actually fit 16 characters. So if we do 128 divided by 16, can't do number. That means we need to do 8-bit integer. So we need this one. Yeah, we need this one. All right. Can you copy it? So what we want to do is use this. Comment that out. Because we're not ready to use it. That's what we, right? And then it's probably going to store, that should have 6, for us it should have so it, like, we should be able to fit 16 integers in there, and it's going to do all 16 comparisons. And so the result is going to be, we would have to like, yeah, sorry, I can't say the words, but the result is going to have 16 results in it, if that makes sense. Yeah. I think to make this a little easier on ourselves, we don't have to do this right now, like while we're just exploring how to do this stuff. I think what we can do is oh, my pen was still on my tablet and that was messing up what the mouse could do. We can comment out all this stuff and about this stuff too. Okay. Okay. Hopefully that sounds doesn't. Otherwise, we got a little ASMR going on. Right. And we can just create 2 strings. And let's just make this. Yeah, let's make it 16. So Give me a B, C. What's 16 in it? Well, D. All right, that's where E, F, G, G, H. H, right? So that's now we're at 8. A, B, C, D, E, F, G, H, I, J, J, K, L. Now we need one more. L, N, O, P. All right. Putting all my skills to the test here. And then let's do the exact same string, and we would expect so that we have kind of like a really predictable result. And then we are going to take this, but instead of that, we're going to do we're going to duplicate that one. Yeah. Why don't we do the A and terrible variable naming? Maybe, I don't know. Okay, and then we want to take this. All right, let's do this. Oh, I already closed all my stuff. Yeah, boy. Was that loud? I'm joining my friends. So I may be chatting to them, but I'm still gonna look at it. What's up,
Yo.
Brent?
Hello.
Hello.
How do I sound? I mess with stuff.
What's up?
Do I sound okay like last night, or did it change?
You sound great to me.
Okay, cool. I kind of moved some things around, and I was worried.
Got it. I hear some echo. Is that me?
Was that me?
Oh, maybe it's me. I hear Matt kind of cutting out a little bit.
Oh, you hear me cutting out?
Not right now, but it's like just like here and there.
Okay. It might be if I lower my voice too much, it won't make it through the sound gate. Probably what that is.
Mm-hmm.
I could probably dial that in. How's your Friday?
Not
Pretty
bad.
good. Yeah.
I'm doing
How about you?
some awesome coding right now.
Oh, nice.
But when you guys
Or
switch to Fortnite, I'm gonna play Fortnite.
Oh yeah, we are playing Fortnite.
I thought I saw you on. For some reason, I thought you were on League of Legends.
I think it's because I just have the client open.
Oh, okay. All right. Well, let me just run this code one time, and
Cool.
then I'll come play. You guys play one match without me, but I'll chat.
All right.
don't forget to change it to duels, I think.
Why doesn't it let me change it? So weird. Okay.
Is it still being weird?
Yeah.
All right. Be right back.
Okay.
Cool. Maybe I can leave and then.
Okay. I was chatting with some friends there real quick, but just to wrap up what I'm doing code wise is so we were doing compare greater than, right? Compare packed for greater than. We're not doing greater than or equal, only greater than. So this result here in our result, it's all zeros, and that makes sense because we did the exact same string. So there's not going to be greater. But if we were to go and switch up our code here and be like, V works too. Yeah, let's go for that. I was gonna do B works, and then we compile that again. Okay. So now what we expect here is to have one element in our result that's one. It's not. Ah! Huh. So that result is not what I was, which sucks. Oh wait. No, values are all zero. So let's clear these. Just gonna look at these in memory. Copy value, paste all the stuff. We just want the address. Okay, and we can see it goes yeah, we can see it has all the parts of our string in it, so that's cool. And I'm sure if we do this for B, it's gonna be the same thing. Okay, so V. So what I'm expecting is that it would be comparing greater than, it would be comparing V to A, which should be greater than. We can see V is 77.6 in hexadecimal. And I really need I need two memory windows. In fact, I'm gonna go ahead and do that because I said that more than once. Memory 2. Put it E. But that's, well, now I just messed things way up. But here we go. Watch. So we'll do SIMD A. This is still not quite what I want. What I want is this. I want like a third. Do I need to like take this one though? There. That's what I want. Okay. All right. So then I want to take this, copy. So let's do A over on this side. We can see we have our string. Put B on this side, same thing. All right, and here we have V through. Let's just put this as 16. 6. Okay. Okay, so we can see both of them here. So, oh, well, no, that doesn't matter. That doesn't. Maybe it compares in a different direction than what I'm thinking. And then if we go here and we do and result, I need a third memory window. Uh, don't give me this. Don't give me this mess again. Why is this so hard? Well, there's a few reasons why it's hard. We don't go with the most obvious. So pull this up here. Like put. Okay. And then we know A, this is A. Need a bigger monitor. This is B. And then I wanted to do the result. Oh, yeah. Right. Result should be, it's nothing right now. All right. Where are we? Oh, wait. Well, the result's all zeros. And I was expecting there to be at least a 1 right here, right? I was expecting there to be a 1 because V is greater than A. So my question is, I probably have to reverse the order of those. That's my suspicion. Let's go read the documentation. Compare or greater than. For 0 to 15, I is A greater than B, true or false? Yeah. Is A greater than B? So we do have to reverse the order. And then let's go compile that. Now let's step through this again. Our addresses are all messed up, but this time we don't really care about that. We're just praying that there's a 1 here. All right, let's do F. Oh, yeah, there is. There is an FF. That's true. Okay, it's not 0. Yeah, it's not quite the order I was expecting. Like I kind of since it's but the Indianness might. So let's do. I just wish there was a way to say, okay, show me this in the memory. Like seriously, why can't I just be like, go to the memory? There's got to be a way, right? View in the memory. Like, where's the thing say view in memory? Dumb. It's a missing opportunity if it's not there, right? Copy value, and then you copy the value and you paste it here, and you have to delete all this stuff. All right, so A is here. So I don't know. I'll have to dig into it a little bit more, but I was kind of expecting for the FF to not be where it is. I was expecting it to be but I'm sure if we think about it, sure if we looked at the code, or if we looked at this SIMD thing or the documentation, we would probably understand that, this is how we're seeing it in memory. But you can see it goes from low to high. Like as you read from here left to right and down, you're going to higher memory addresses, and if you go up, you're going to lower memory. So let's take a look. Let's take a quick look at this documentation. This syntax for me is like super hard to read. I don't totally understand it. It's doing a at I plus 7, which I is equal to j. So if j is 0, then I is 0, and then you're doing plus 7. And then, so why would that give us a result that's kind of, I don't know. That's something that I'm going to look at later, but for now, I'm going to stop looking at programming and go play some games. To wrap it up, I think, this started out with looking at this LeetCode problem, 944. And, you're just supposed to look at these strings, and if like C, D, G is not alphabetical order, then you mark that for deletion. It's kind of an easy problem, but what we're really looking at is, can we use the SIMD instructions? And so far, it's looking like we can. So next time I work on this, I'll probably take the next step at implement. So for now, I'm going to go ahead and stop programming and probably switch over to playing Fortnite. Yeah, I'm gonna go ahead and end this. Came by and watched. Thanks a lot, and I will see you next time. Bye.